In this video, we're going to be discussing level triggered D-type flip-flop. Level triggered being because there's a certain level that is needed for it to remember something or to remember a certain bit. D-type because its input is known as data input. Okay. So we have to remember the specific circuit that we were able to construct in the previous video. Okay, so this is the RS flip-flop. RS meaning that it has a reset and set inputs. So what happens here is that if we set S to 1, it remembers the output of 1, and if we change the S back to 0, it doesn't change things. It remembers the previous output. All right. So it remembers the last input where there's a certain one value inputted. All right. So if we input a value of 1 for reset, it remembers the value of 0. So regardless if we change the reset back to 0, it remembers the value of 0 still. Okay, so it remembers the value of the previous state when the state is 0 and 0, or when there is no input anymore. All right, again, the RS flip-flop does not allow a one-in-one configuration for set and reset, just because the output Q and the inverse output bar Q will no longer be inverse each other. So Q and bar Q is no longer being true. So that is disallowed, or this is the when designing an RS flip-flop, that is to be considered not legal. Now, what we want is to be able to control when the circuit should remember in a specific level. Okay, so we have this an input of hold that bit. So what happens, as mentioned earlier, if the hold that bit is in 0, it does not remember the data input, or at least it remembers. It doesn't change it. I mean, it does not store a new value from the data input. It remembers the old value. Now, if we change the hold that bit to 1, we will level trigger it with the value of 1. So what happens is when we change the hold that bit to 1, the data is being remembered as 0. Now, if we change the hold that bit back to 0, whatever we do, it remembers the previous value stored. And vice versa with the input. When we change the input value of data, while we hold that bit value to 1, remembers this current state. Remember, it stores this current state. So if ever we change the hold that bit value to 0, regardless if we change the data input to 1 or 0, it remembers the old value. It remembers 1. Enter the level trigger D-type flip-flop or latch being because it latches onto a certain output of the circuit, which is memory, which latch is also means computer memory. Level triggered because the circuit is triggered to remember a specific output when the hold that bit input is on a certain level. Again, we'll discuss this. So we'll discuss a specific circuit with the trigger level of 1, D-type, because the main input to be remembered by the circuit is called data. Okay, so this is our circuit for D-type and level triggered flip-flop or latch. Okay, so our initial state requires us to hold that bit value and a value of data of 0. So what happens is the inputs is 0 for hold that bit, and data of 0 and 1, because there is a NOT gate here. So 1 one AND gate is receiving a 1 input, and the other AND gate is receiving a 0 input. Okay, so 1 and 0 becomes 1 and 0 becomes 0. Okay, so we must remember that. Okay, and 0 and 0 becomes 0 and 0 becomes 0, right? Okay, so initially the state of the first flip of the first NOR gate, we have a value of 0, just because initially there is no current flowing here. So what happens is 0 or 0 becomes 0, invert that becomes the 1. So our output becomes the 1, while this output is being fed back here, and it becomes the 1. So 1 or 0 becomes 1, and not inverse that becomes the 0. So this becomes 0. So it becomes 1 and 0. Okay, so this is our initial state of our circuit. So again, the first output, the first output becomes this becomes 1, and this travels here, it becomes the 1, and this travels here, becomes the 0. So what if we want to change the value of the output? So what we need to do theoretically is we need to get to. Okay, so let's understand first that nothing changes if we set the hold that bit of 0. So regardless of we change the data to 1. Okay, let's change the data to 0. So we'll be testing this specific truth in this truth table. So we should be able, theoretically, if we don't change the hold that bit to 1, or if we don't level trigger it to 1, the output remains the same. So let's see. Okay, so data, so it goes here, this goes here, and this goes here. 0 goes there, and then the data, this is inversed, so it becomes the 1. Now 1 and 0 becomes 0, and 0 and 0 becomes 0 still. So 0 or 0 becomes 0, inverse that becomes the 1, and 1 or 0 becomes to 1, inverse that becomes a 0. So we were not able to change the output because the hold that bit remains the same, or remains 0. Now if we level trigger that, then we'll be able to change the output. Now what we want to do is change the output. So we're gonna try to change the output from 0 to from 1 to 0. So we're gonna do this specific truth in this truth table. So we have a data of 0, and we have a clock of 1. So essentially, theoretically, when we set the hold that bit to 0, we are allowing changes or a new data to be stored, a new bit to be stored. Okay, so since we allowed that, and we also changed the data to 0, so we can expect that our mean output becomes 0. All right, so this becomes 0, this becomes 1 and 1. So 0 inverse that becomes 1, 1 and 1 becomes 1, 1 or 0 becomes 1, inverse that becomes the 0. So this travels here, this becomes 0. So 1 or 0, 1 and 0 becomes 1, 1 or 0. Wait. Okay, 1 and 0 becomes 0. Okay, so 1 or 0 becomes 0, inverse that. 1 or 0 becomes 1, inverse that becomes 0. This output feeds fed back to this other output, and this 0 or 0 becomes 0, inverse that becomes to 1. So essentially, we have changed the output or the stored value of the circuit by setting the hold that bit value to 1. Okay. Next, we're gonna change the value back again, or let's test again if we set uh, the hold that bit value to 0, if it retains the value of 0 for the output. One more thing, since we have changed the value of this to 1, it travels back here and becomes it's being fed back to the other NOR gate and becomes 1. But still, 1 or 1 becomes 1, and reverse that becomes a 0. So the circuit still settles down to 0 and 1 for the outputs, respectively, for the Q and Q bar, right? So it settles down to this output. Okay, let's check again this certain truth where there is, if we set the hold that bit to 0 and we set the data back, let's say we change it to 1, let's see if the output is being changed or not. Theoretically, it will not change because hold that bit is still set to 0, or what we also call the clock input is being set to 0. Clock being because hold that bit input we can input a clock or an oscillator to the hold that bit input to be able to automate the process. Okay, so let's say that the hold that bit value is 0, so this becomes 0 and this becomes 0, and this becomes 1, and this becomes 0. 0 and 0 becomes 0, and 0 and 1 becomes to 1 again. So 0 okay, so from our previous value we have 0 and 1, so this becomes 0 and or 1, this becomes 1, and inverse that, wait, I mean 0 and 1, this becomes 0, so the output of this one is 0, or 0 becomes 0, inverse that still becomes the 1, and the input is fed back still 1, so 0 or 1 becomes 1, and inverse that still becomes a 0. So what we proved here is this truth is still true, because the truth that if we don't set hold that bit to a certain level of 1, the circuit is not being able to store a new value. It retains the old value. All right. Okay, so now we're going to prove that if we set both the hold that bit and the data to 1, we will be able to change the output. We will be able to store the value of 1 on the storage or on the output. Okay, so what the inputs we need to have is the hold that bit should be level triggered of 1, and the data should be 1 in order to change the output to 0, or to store a new value of 1. I mean, to store a new value of 1. All right, so we have a value of 1 here, and we have a value of 1 here and 1 here. Well, there's a NOT gate here, so we have a value of 0 there. So 0 and 1 becomes 0. Well, 0 or 1 becomes 1. Inverse that, it becomes 0. Well, 1 and 1, we have a value of 1. So 1. So what we have a value of 0 and 1, or 1 or 0. So inverse, so it becomes 1 or 0 becomes 1. Inverse that becomes a 0. Now another feedback is traveling back to this other feed to this other NOR gate, and now the the feedback becomes 0. So 0 or 0 becomes 0, and rheostat becomes to 1. So it settles down to an output of 1 and 0. Now, if we continue on with analyzing the circuit, we see that this feedback becomes to 1, and this becomes 1 and 1. So 1 or 1 becomes 1, and inverse that still becomes 0. So essentially, everything settles down to 1 or 0. All right. So we have essentially proven all three of these truths in our circuit. Next video we'll be discussing how to use the D-type level triggered flip-flop or latch on with our other circuit.